Thank you. Yeah, I will be talking about the ups and downs of spectroscopy. Pun very much intended. I was very pleased with myself when I came up with that. Yeah, so there's a lot of really cool things we can do, but there are also a lot of challenges. And besides the fact that planets are small and faint, and I'm going to talk about the challenges and how we're dealing with them and attempting to deal with them. So why do we do spectroscopy, not just of exoplanets, but of planets in general? It's because it's the best way to learn about, especially for exoplanets, where we cannot just go send a probe and sample the atmosphere directly. Best way to learn about exoplanet atmospheres. We can get information on stuff like chemistry, molecular abundances, temperature scales. In the future, it's even possible we might be able to determine whether or not there's life on other planets using spectroscopy, which is, I mean, this isn't just science fiction anymore. This could actually be doable. Probably not going to happen anytime soon, but fortunately, there are a lot of really cool things we can do in the meantime. We can learn about more on how planets have formed and how planet atmospheres evolve. All right, so most of my work has been done with high-resolution data. And in the era of JWST, the question is, well, why do we still use high-resolution data? The data is incredibly high-resolution spectroscopy, just in general, is very, very information-rich. The high-resolution transmission spectroscopy can be used to learn about planet atmospheres, but can also be used, the exact same data set can be used to measure the Rossiter-McLaughlin effect. So that's really cool. There's really more data in any of these, a single transiting data set that we can learn about. I'll talk about a recent paper that I published, and this was done using archival data with the very end of the wavelength coverage. That it was not taken for this purposes, but because high-resolution spectra are so information dense, we're able to readapt it for our purposes. Another advantage of high-resolution spectroscopy is each chemical species has a very distinct signal. There's no degeneracies between, say, CO and CO2. So it's much easier to uniquely identify any given atmospheric component. There's also, JWST is great, but there's only one of it. It has a few instruments, but there's not a ton of instrument wavelength overlap. With high-resolution data, there are not a ton, but there are a lot of instruments we can use, and we're able to more easily verify our work, which is always a good thing, because with these, especially marginal detections, that verification is extremely important. Velocity information with high-resolution data is preserved. And I'm going to talk a lot about this throughout the talk. But most of these spectrographs are good to 1 to 2 kilometers per second. And we can use that information to do a lot of really interesting things. And I'm an observational astronomer. In my opinion, more data is always a good thing. So, yeah. All right. So I've talked about the whys of high-resolution spectroscopy. I'm going to talk a bit about the hows. So the basic process is, the first thing we have taken data across transit of an exoplanet with some pre-transit data, some post-transit data. The first thing we want to do is remove the stellar and telluric features so we can see the planet, because obviously the star's signal dominates. And then the tellurics are also significant depending on the wavelength region. There's a couple ways to do this. The most common way is basically we use the fact that the planet orbits at very high velocities, sometimes hundreds of kilometers per second. And so the planet's signal across a transit can shift by 20 to 30 kilometers per second. And at the resolution of high-resolution spectroscopy, that's across a bunch of different pixels, while the star signal stays within its own pixel telluric signals stay within their pixels. So basically, if you subtract the median approximately, you remove the star signal, you remove the tellurics, and you'll be left with just the planet signal. An example here, raw data is on top, and blaze corrected is on the middle, and the bottom is our removal of the telluric and stellar lines. We do this in a process, a PCA-like process called singular value decomposition, but basically we're just subtracting a fancy median. The other way that's commonly done is to use either a telluric standard or to do radiative transfer modeling of the telluric lines to remove the tellurics. In this case, it's unlike with SVD or PCA, where we remove the tellurics and the stellar signal in one go. In this case, we remove the tellurics first and then remove the star signal. Again, this is fake data, as you can see. If our data was this clear, we would not need to use big telescopes. But in the top plot, the star signal is the overwhelming one. But once we start to subtract out a median, the planet signal, which is there in the top plot, but it becomes very evident. It does not subtract out because it's been taken at 4 different epochs. And so the Doppler shift allows us to keep the planet signal. Once we've done that, we need to, because the signal is so weak, we cross-correlate the data with a template to combine the signal from all the lines into one strong signal that we can detect. This is most commonly done, but for stuff like sodium or hydrogen, where there's only 1 or 2 lines, we can skip this step. For most species, things like iron in the optical, CO, and water in the infrared, there are hundreds or thousands of lines, and any given single line is not strong enough to detect. But the combination of them, we could potentially detect, and so we do so. And then we have to co-add the spectra. We co-add all the spectra taken within the transit, and we don't a priori necessarily know the inclination, so basically we just try them all, which is equivalent to trying different planet velocity amplitudes. And as you can see on the graph, as we step through inclination and Kp is planet velocity amplitude, the spectra eventually become aligned, and then they co-add coherently, and the cross-correlation function ends up being at its maximum. And after that, we make pretty plots. This is an example from my recently published paper of chromium hydride. With the planet velocity amplitude, as I said, we're stepping through. Each row is a cross-correlation function, and we get a detection of, in this case, chromium hydride. We'll talk a little bit more about that later. It doesn't have to be like this. For stuff like sodium or hydrogen, we still step through the different inclinations, but we can just use wavelength across the x-axis. And this is a detection of what we believe to be sodium. But often for stuff like transmission spectroscopy for sodium, we just take a crosscut at the correct Kp value and plot a transmission spectra. And yeah, so that is how we're able to detect molecular or atomic species in high-res data. Yes. Yes. So it's the 2 dark blue blobs. Those correspond to the sodium, flux decrease from sodium. Yeah, I'm going to talk more about both of these later on. I just wanted to show an example of how we do this. All right, so that's the basic setup, and it's fairly traditional. Most people doing high-res spectroscopy do it in very, very comparable ways. Sometimes the details are different, but the overall process is the same. So I was hired to work on a survey that we've dubbed Exogems, a survey on Gemini North with gray seas. What's cool about gray seas is that it goes further red than a lot of optical spectrographs, going out to past 10,000 angstroms, actually. But it's useful in the red, where stuff like HARPS and espresso get cut off shorter than that. We've observed 25 planets in transmission, with hopefully 10 more to be observed in the future if Gemini decides to be nice to us. Our time has been cut short because Gemini has been broken and then hacked, and it's been a lot of fun things. But the goal of the survey was to explore a large range of temperatures and masses, not just go for the ultra-hot Jupiters. Yeah, so some of our results from the survey. Our first result was published in 2021 by Emily Dybert. Confirmed sodium in WST76b. This is a favorite of high-res exoplanet people because we can detect 3D information of the planet's atmosphere, which is really cool. Because, but she was also able to get a calcium infrared triplet. This is one of those ultra-hot Jupiters. Followed up with a paper recently published that shows that there's no titanium, which is surprising because typically objects of this temperature have titanium. And the theory is titanium is sequestered and condensates via titanium cold trapping. All right, so that's one of the ones on the hot end, hot big end. On the slightly smaller end, we have GJ3470b, and we have in yellow what we believe is a tentative H2O detection. Now, the tricky thing is with eccentricity is that eccentricities are often not well measured. There's a fairly large uncertainty on them, and this uncertainty propagates into the graph. So if we don't know exactly what the eccentricity looks like, we don't know exactly what the signal looks like. And you can see that depending on the eccentricity assumed, the signal shifts. As you decrease this assumed eccentricity, the yellow signal shifts downward and to the left. And that limits our ability to characterize this, the water in GJ3470b. This is one of the, as I said, interesting things with the velocity resolution, because it's not a huge shift, but it is one that's detectable at with high-res spectra. And I should note that you really don't need a large uncertainty in eccentricity to get fairly significant offsets. Eccentricities, uncertainties of 0.1 are not uncommon, and those are off this graph. This is a work done by an undergrad I'm working with because of the GJ3470b data set. I was like, well, how does this affect? Can we quantify this effect? And it's dependent highly on angle of periastron. But basically, even for if you're off in your eccentricity by only a very, very small amount, say 0.05, which is, I think, a pretty good uncertainty for eccentricities as measured by radial velocities, you can get 7 to 8 kilometers per second offsets. And that can be a signal that's dismissed as fake or interpreted as, say, winds. If we see blue shifts in planets, we attribute that to winds. And it can also just decrease the quality of the signal. So there's a lot of complications induced by these eccentricities. One of the downs of high-resolution spectroscopy, but it's also useful because it requires us to really understand the planet's orbit. All right, on to this is a bit of a pet project of mine. So we went from very big to slightly smaller. This is kind of in the middle, temperature-wise. When I started this project, one of my goals, personal goals, was to be able to detect chromium hydride or iron hydride. These had not been confirmed in any exoplanet yet, which is a bit surprising because they're ubiquitous in brown dwarfs of the same temperature, to the point where they're used to determine spectral type. As you can see here, just to the right of the yellow line, the chromium hydride feature gets stronger and stronger as you start getting into the L band, and then starts weakening as you exit the L band. That's because it's the chemical equilibrium abundance of chromium hydride is very sensitive to temperature. So it basically works as a really great spectral type indicator. Same with iron hydride. So we expect these to be in exoplanets, but we have not yet been able to confirm any detections. There had been some tentative detections with low-res data, and one of those was in WST-31b. So there was a 3.9 sigma detection of chromium hydride from Brahm et al. 2021, but that 3.9 is making a lot of assumptions, and we would like to be able to confirm it to say for sure whether or not there's chromium hydride in this. So in March, I put in a request as part of our survey to do this, to observe WST-31b with Gracies, and in March 2022, we got one transit of Gracies. And I searched for a lot of things because that is part of the pipeline, but one of them was chromium hydride, and we were able to get a 4.1 sigma detection of chromium hydride with Gracies, which I was very, very excited about. However, for high resolution data, we generally try to hit 5 sigma. This is because while we put this lovely 4.1 sigma number, we seem to have a larger number of false positives at the 3 to 4 sigma level than one would suggest by a 4 sigma detection, which suggests we should really not have any at the number of published papers with that. So we really try to hit 5 sigma. And because of the difficulties with Gracies and Gemini, getting more data through the program has been not successful. But I got really lucky on this one. There was archival UVES data of the system. Oh, I should mention, so while this is a slightly weak detection, I did all the sanity checks. Like, it's in both half of the transits. You see it in multiple orders of the spectrograph. So it's completely consistent with a weak signal from a planet. It's just weak. Right, but we wanted more data. And fortunately, so Neil Gibson published in 2019 a paper of non-detection of potassium on this planet. He had put in for UVES observations. That's centered at 770 nanometers. And the very last order, at the very edge, we get this lovely, we get 6 nanometers of a chromium hydride band, and he has 2 transits of that. This is on the bottom I've plotted the chromium hydride template. We don't like the band head around 764 nanometers because that is contaminated with oxygen. We like the one around 860 because it is not contaminated with oxygen tellurics. And we got 2 transits of that. So when we combine all the data together, we have Gracies on the top, UVES night 1, UVES night 2, and the combined UVES data on the bottom. And Gracies is at about a 4 sigma, and the UVES is about a 4 sigma. The 2 4 sigma detections plus the low resolution data, I was pretty convinced. I should note that you can see that these detections aren't quite at the same point in the graphs. That worried me a little, and to be honest, still does, but there are a lot of very plausible explanations. We see this, unfortunately, a lot. And one of the potential reasons is that we don't know the transit ephemeris that well. And like the eccentricity, if you don't know the transit ephemeris, if you're off by a handful of minutes, which is not unreasonable, you can start seeing offsets. Further work by Yasmin, she calculated what the velocity offset would be depending on a certain typical hot Jupiter. And if you're off by, say, 4 minutes, you could see velocity offsets around 2 kilometers per second. Again, the velocity information is very, very important here. And this is not just the simulated data. If we go back to Emily's the first detection I showed with Emily's sodium detection, this is co-adding both lines together. But you can see this with the ephemeris she assumed from her 21 paper, the line is about at a velocity of 0. And with the new ephemeris plotted on the bottom, there's a slight blue shift to the data. And this is real ephemeris, real data, and you can see several kilometers per second offset. Just in determining, proving how important getting the correct ephemeris for transit midpoints are. All right, so back to the Gracie's chromium hydride. So to confirm this and combine the data sets, we didn't want to combine them directly because there are 2 different resolutions and they cover 2 different wavelength regimes, and that makes things very, very difficult. Instead, what we did was just combine the probabilities. So what we do to determine a given probability for a data set is to use the out of transit data, and we simulate 20,000 transits with the out of transit data. And if our signal is stronger than most of the out of transit data, that's a good sign that our transit is not spurious and it's just a coincidence because of the noise. And in our case, for Gracie's data, our signal was stronger than all but one of the 20,000 simulations. In the case of UVIS, it was stronger than all but 5 or 6 of them. So we combine that together and we get odds of about 1 in 67 million. And that's good. I mean, assume a Gaussian distribution that's about a 5.5 sigma detection. So we can, in fact, confirm there's chromium hydride in WST31b, which is awesome. This is the first metal hydride confirmed in an exoplanet, and I'm really excited. And I am very much hoping that people will look in their PRISM, JWST PRISM, and NIRISS-SOS data sets and start looking for chromium hydride and iron hydride, because it really should be there. And I think it's going to be a really interesting and potentially useful detections to see if it mirrors what we see with brown dwarfs. All right. So one of the interesting things with high resolution data, because we have that velocity information, is that we're really good at telling if there's stellar contamination. I'm just going to say this now. That doesn't mean we can always do something about the stellar contamination, but it's much easier in high resolution data to tell if there is stellar contamination, as opposed to lower resolution data where you get degeneracies. So in high resolution data, you get this very characteristic V shape, where it's strongest at around Kp equals 0, and just flares, basically makes a V upwards. And because we have this velocity information, we're better at getting rid of false positives. So on the bottom, this is a cross correlation. There's a faint horizontal line, the cross correlation function at that. At lower resolution, one might see this and think it was a detection, but because the signal is only offset by 10 kilometers per second. But because we have this high resolution data, we can see that it is in fact a false positive and it's not a real signal. And the way we handle this, especially Emily from her 2021 paper, 2021 paper, is the best way is typically by masking out the cores of lines if we get enough velocity shift across the transit. You can also, depending on how you deal with the stellar activity, changing methods. Sometimes different methods works better for stellar activity versus others. But as I said, we're very good at diagnosing it. So an example of this is WST85AB, one of our other targets from Exogems. Obviously, stellar activity is going to come into play here. This is its light curve. It's a young, and by young I mean 1 gig a year. If the planet formation people heard me referring to a star at 1 gig a year as young, that they would have a connection fit. But for exoplanet atmospheres, 1 gig a year is in fact young. It's a young planet host and also has a nearby companion and lots of stellar activity. And we're able to, so this is the sodium detection I showed earlier. You see sodium in both lines around a Kp about 100, both sodium features. But we wanted to make sure this wasn't stellar activity because there's clearly a lot of stellar activity. Oh, I should note, again, here's the transmission spectra if you do a crosscut. So to confirm that this isn't stellar activity, or at least not mostly stellar activity, we look at how in PCA you remove different number of components. And if you, so on the top plot, we've removed 5 components, the 5 main components. Just basically subtracting a median 5 times. Slightly fancier than that, but yeah, approximately that. If you only subtract a median once, 1 component removed, you get the plot on the bottom. And we see, it's harder to tell because it's not quite a V shape, but there is that signal that peaks at Kp equals 0. And it is, I mean, sorry, we don't have the wavelength coverage, but it is slightly in the V shape. So there is stellar contamination, but it looks like we've done a pretty good job of removing it. That doesn't, I should note that we have 2 transits of this, and we see the sodium in both transits. And so I've done this with SVD, and my collaborator Adam has done this with MolecFit, a completely different method, and we both see the sodium. So we think despite the stellar activity, we're fairly confident that this signal is from the planet, or at least mostly from the planet. It's hard to say if it's 100% the planet or only 90% the planet, and that makes it tricky to tell. But because we have this velocity information, we can be very confident that it is the planet and not the star, because we see where the star's signal was. So stellar contamination is especially an issue for transiting planets, because assuming you don't have a large eccentricity, when the planet passes from the star, it has approximately the same velocity, Doppler velocity, as the star. So their lines will overlap in Doppler space. If you're doing emission spectroscopy, this is less of an issue. And by emission spectroscopy, I mean like emission taken at like 1 or 2 o'clock on the orbit. You get a much bigger separation in velocity space, which you don't necessarily get for transiting exoplanets. So this is an example of emission spectroscopy with a ton of stellar contamination. This is emission spectroscopy from a classical T-Tauri star. And this would not be doable with transmission spectroscopy, A, because the disk would probably get in the way, but B, because all of that stellar activity, you can see the V shape, but because it's not in transit, the V is wide. We're able to find a detection in the center of the V despite that. I should note, I'm still very proud of this. This is a slightly old paper now, but we're able to detect CO and CI tau B. It's, I think, the youngest confirmed hot Jupiter out there still. We were able to show that it formed with hot start formation. If you plot its magnitude of the planet versus the age, it's that one up there. And at 11 Jupiter masses, being right above the 10 Jupiter mass hot start formation line is exactly where you'd want it. And so that was really cool. But this is not doable with transmission spectroscopy. Yes? Yeah. So yes, this is interesting, and it just obviously we don't think it formed it's at 0.08 AU. It would have to have migrated in, and disk migration can happen pretty quickly. So that's not the issue. That there's, I mean, theory shows that disk migration happens, and it is not the only hot Jupiter. There's evidence of hot Jupiters around like slightly older, like 3 or 4 million-year-old systems that are in transit with not a classical T-Tauri star, but weak-line T-Tauri stars. So clearly, it is possible for Jupiters to get in there by that age. This is not the only example. Hot start, that's interesting. It's controversial controversial because that obviously points to slightly more gravitational instability explanation. But at 10 Jupiter masses, gravitational instability is still very much a viable theory. For smaller planets, gravitational instability becomes less practical, but I mean, this thing's practically a brown dwarf. We think that's a perfectly viable explanation. Obviously, there's further work that can be done. This alone doesn't confirm it, but it paints a consistent picture. Right. So I said we're much better at diagnosing stellar activity, and that's true, but we can't do it perfectly with high-res data. This is a case of iron in GJ436b. And so for planets around low-mass stars, the signal becomes more and more vertical as you go to smaller masses because the planet velocity orbit becomes slower and slower, so you don't get the velocity spread. We know there's not iron. Well, we're pretty sure there's not iron in GJ436b because it's at 800 Kelvin. So we're fairly sure this is from the star, which is not surprising. It's an M dwarf. It's active. But for molecules like water, where it is less, it could be in the star or the planet, not having as wide a V shape can be difficult. And that's especially annoying because for the systems that are most affected by this are, as I said, planets around low mass stars, like M dwarfs, which are, of course, the most active ones, and most likely to induce stellar activity signals. But again, we still have some information in that and some way to track the whether or not it's stellar activity. Right. But obviously, so the best way, like in an ideal world, to detect, to characterize the stellar activity and whether or not to what extent it's contaminating our transmission spectra would be to do UV simultaneous monitoring. It's not practical to do UV simultaneous monitoring for all the exoplanet atmospheres observations. Although I'm guessing I'm at NASA now. You guys want to fund 4 or 5 UV missions right now to start doing that? I'd be very happy with that. But I figure that's unlikely to happen. So one thing I tried to do is there a way to track the UV data with the high-res data we're getting? Because we have, when we're taking high-resolution transmission spectroscopy, we're taking with that high-resolution observations of the star. So what can we learn about what the star is doing through those observations, even if it's just minimal levels of activity? So for this, we use the HARP Sun as a Star observations. There's 3 years of public data. I should note that this study was done by my student, Nicole Howe. Based on what we saw with WASP 85AB, I saw that I was just like, there has to be a better way of tracking if we can track whether or not this was likely to be affected by stellar activity. So these HARP Sun as a Star observations, they're taken for about 5 minutes, so it's comparable to the time scales for your transmit. Each observation is 5 minutes, comparable to the time scales for transmission spectroscopy. This is an undergrad summer project, so we limited the wavelength range and used PCA to speed up the classification. And we used a support vector classification algorithm with a polynomial kernel. This is just a way we're classifying our HARP spectra to start out with into strong flares, weak flares, or no flares. And the support vector classification basically just draws decision boundaries between the 3 groups. And so we want to see, so there's no visible flares in this data. At this is the data of the sun. The sun doesn't flare that strongly, and high res basically smears it out. We wanted to see, could we detect flares despite that? And we used HESI, flares database, and so we could cross-reference which spectra were taken during flares and which spectra were not. And a blind classifier would classify each group with 33% of the time, and we're able to get up to about 60% of the time. So this is a confusion matrix for classification. And ideally, it would be 100 across the diagonal. We're not there. We're at lower levels. But as you can see, most of the time, we're able to detect weak flares and strong flares in our data, despite the fact it doesn't, by eye, look like the data has flares in it. This is a significant improvement on blind classification. She tried 2 different kernels, and the polynomial kernel was the best one. And she is writing this up as a paper right now, probably as we speak. All right. So I've talked a bunch about high-res data, and over the past, I guess, 6 or 7 months, I've actually had an opportunity to start doing similar things with JWST data. Because unsurprisingly, stellar activity is still affecting JWST data. This is an example of one of the many, many flares we've seen. And I'm working on a group with GTO time that's observing TRAPPIST, several of the TRAPPIST planets. And one of the many flares we've seen that is contaminating our TRAPPIST transit spectra. Like about 50% of our transmission spectra have stellar contamination from flares. Not a good ratio. It's also granulation, and so those are the temporal effects that we've seen clearly. And from a spatial aspect, so this is 2 visits of the same planet, and transits look similar, but if you look at the short wavelength regions, they look, there's clearly some differences, especially at the shorter wavelength regions. And this is very likely due to the fact that the star has spots or plages, and transmission spectroscopy generally assumes a uniform surface, which TRAPPIST-1 is not. All right, so what are we going to do about these things? I don't have answers yet. We're just in the process of answering this. This is a fairly new project. So the first, for flares, this is broken up into 2 stages. The first is diagnosing what we're already doing. Is it good enough? The answer is no. It's not good enough. We see so residuals, once you've done the light curve fitting, should, in theory, be nicely Gaussian. And as you can see, especially from the bottom plot, these are not necessarily nicely Gaussian. The residuals are skewed. And worse, they're skewed with a wavelength dependence. And so if the residuals are leaving wavelength dependence after the flare correction, and we tried 4 different methods for correcting from flares. We did a GP process, H-alpha determined flare correction, and then just a model-based physics flare-corrected data. And it doesn't matter. We still see this basic shape of wavelength dependence in the residuals. And whatever this wavelength dependence is, this gets pushed into the transmission spectroscopy that could be misinterpreted as a planet's atmosphere. So this is in wavelength dependence. We also see, unfortunately, lots of not an insignificant amount of time-correlated red noise from even after removing the flare. So this is just the stage 1. Stage 2, which we've just started, is now that we've evaluated it and know that what we've done previously is not good enough. Stage 2, we're going to be is to find something that's better. We started on some things that I'm not going to talk about because we're not quite sure to what extent they're working yet. But we are making progress in that area, and hopefully are not going to be forced to throw out half our transits. All right, with regards to spots and plages. So again, transmission spectroscopy assumes a uniform disk. This is not physical. Even for the sun, we know that's not physical. And this is especially difficult to deal with for low-mass stars because low-mass stellar models are not good. Oh, yes, as I said, this is TRAPPIST-1. We're currently doing modeling this out, doing this 2 ways. One by modeling the transmission spectroscopy and the stellar contamination simultaneously, and one by doing the contamination first and then doing the transmission spectroscopy. They're fairly equivalent. They're both able to get out a planet atmosphere that is basically flat. But there is some mismatch from the data. And one of the main reasons we think is that the stellar models for TRAPPIST are terrible, like really, really bad. These are the state-of-the-art Phoenix and Sphinx models, and you especially can see around between 1.3 and 1.8 microns. There's a huge mismatch. Sphinx is doing a little better around 1 microns, but this is real data that we cannot fit with models. And if we're trying to use these models to model the photosphere so we can judge to whether or not they have spots or plages, that's going to be a problem because spots or plages are going to induce signals probably smaller than the discrepancy in the models between the model and the data. So a lot of really smart people are working on this, and I was actually not going to. I only started dealing with this because I was frustrated with the ways we were trying to deal with this. And this is very preliminary. This is about a week old, but I'm really excited about this, so I'm going to share it anyhow. We're able to. I'm working with someone who does brown dwarf modeling, and because TRAPPIST, it's like an M7, M8. It's pretty much a brown dwarf, not quite, but we're trying from the ground up, and we're actually able to model the 1.3 to 1.8 micron range much better than the Phoenix or Sphinx models. So this is very preliminary, but I'm excited to I think we're going to be able to improve on what we've done thus far. All right, so I've talked a lot about stellar contamination. I now get to talk about the other major type of contamination, which is telluric contamination. And this is what we have. This is fortunately, unlike stellar contamination, not an issue for JWST data, but it is an issue for any ground-based data. Right. So telluric contamination. This plot shows atmospheric opacity as a function of wavelength. Obviously, in the radio, we get all the light. In the UV, far infrared, we get none of it. And then in the optical and near to mid-infrared, we get some of the light. And what percentage of the light we get has a strong wavelength dependence based on the molecules in the Earth's atmosphere. And this wavelength dependence leaves traces in our data if we don't perfectly correct for it. So we like to do as good a job as possible correcting for it. So I talked about earlier how we do this. I'm going to just go over it again. We can use quickly, as shown on the right here, a telluric standard or Malek fit to model it out. For time series exoplanet observations, we can use PCA, SysREM, or SVD. But none of these things work that well. We're still stuck with plenty of residuals. Why that's the case? Well, in the case of Malek fit, apparently radio transfer modeling is hard. Who knew? But also mainly, the Earth's atmosphere varies a lot, and spectrographs are not perfectly stable. So like taking a median in those cases is not going to remove all of the telluric signal. Right, just in general, the deeper the line, telluric lines, the worse the telluric correction becomes. This is an example in the optical showing that the weak lines are well corrected, medium lines are okay corrected, not great. Strong lines, it's a disaster. And this is true regardless of the method you use. To quantify this, it's good to about 2% in bad regions. Not all science cases need to go into bad regions. And this 2% is also dependent on stuff like species, spectrographic methods. So there's a lot of science cases where either you can avoid these regions, or like at Spectra with, at lower signal to noise, this doesn't matter. This is a tiny bit of the noise budget. But as you start pressing further and further in signal to noise, this starts to become more and more important. So you're going to have to know, so the RV community has done a really great job of quantifying how much tellurics affect their RVs. And I say this as a part of the exoplanet atmospheres community. We have not done a great job of quantifying how much the telluric contamination is affecting our RVs, our atmospheric analyses. So you kind of have to take my word for it. But there are targets where we can do really awesome science despite the telluric corrections. And there are targets even today where telluric corrections are preventing us from doing analyses of exoplanet atmospheres. And that's a little disappointing. And this problem's only going to get worse. As we go to larger telescopes in the future, the photon noise is going to drop down. Telluric corrections aren't going to get any better just because you go to a 20, 30, however many meters telescope. Telluric corrections are going to stay at whatever percentage they are because they aren't affected by the telescope's diameter. And this is especially annoying because if we want to have a chance of detecting biosignatures, the regions are looking at an Earth twin with a ground-based telescope, we're going to be looking for lines that are deepest in the regions with the most telluric contamination. So telluric correction is going to become extra important in the future, especially for potential biomarkers. On top of that, PCA, System SVD, as I said, they use the fact that the planet's orbital velocity is hundreds of kilometers per second. But habitable planets are likely going to have, in general, based on what we think the habitable zone is, much lower planet orbital velocities to the point where, so in the bottom graph for a hot Jupiter, the planet signal in white, has a huge amplitude. As you go to smaller and smaller orbital velocities, that line flattens out. And so if you subtract the median, you're going to be subtracting the planet signal along with it. So stuff like PCA, System SVD are going to become essentially obsolete as they now are for potentially habitable planets. So what can we do about that? In recent years, there's been a handful of data-driven approaches to telluric corrections for, again, because the RV community has been really on top of this, optical spectrographs like HARPS. And one of these programs was Wobbly by Megan Bedell. And basically, Wobbly takes advantage of the fact that the barycentric velocity moves the stellar lines in Doppler space, but the telluric lines don't move. So you can determine what's a telluric line and what's a stellar line. It works really, really well for optical data with these fairly weak tellurics, even if that data is fairly noisy. So what I was hoping to do is port this to the infrared, because we do a lot of really cool science in the infrared, and if we're going to be looking for biomarkers, they're likely going to be not completely, but largely in the infrared. This is really tricky, and because there's a lot of difficulties with infrared spectroscopy as compared to optical spectroscopy. Four main ones are continuum fitting is harder because the continuum is less clear due to all the telluric features. Telluric lines are deeper, and as I mentioned, the deeper the lines, the worse the telluric contamination. Telluric lines are blended. This gets nasty where you have the CO2 blended with the water, or the methane blended with the water, everything blended with the water because water is everywhere. And apparently that blend makes it very difficult for radiative transfer modeling. Also, the spectrographs are less stable, and stability is key to being able to model out time series tellurics. Right. Oh, we think we have a handle on the continuum fitting, but we use a model to determine where the continuum should be and only use those points to create calculate where the blaze should be and then correct for the blaze. The rest of it is a bit difficult. Basically, we're just compensating for the deeper blended lines and the lack of stability by doing other things, again, to compensate for it. And the way we do this is by using hundreds of A0s that have already been taken in the archive to create a telluric template. And we can feed this template into Wobbly, and it makes it easier. It has a good, basically, starting guess as to what the telluric model should look like. Makes it the program more likely to successfully find a telluric model. We can also do something similar for stellar spectra. One of these is not updating, but look at the okay. What just happened? Where is it? Did I exit? PowerPoint slideshow? No. There it is. Okay. Sorry, I don't know what happened there. Do I need to share this?
Yeah, if you want.
Sorry about this.
There we go.
All right. Sorry about that. Oh, this is the wrong screen. Stop sharing. Where did? I'm so sorry. I have no clue what just happened. Share screen. Down there. There we go.
Working.
Your screen sharing is paused.
Why don't you stop sharing?
There. There. Okay. Well.
Oh, yes, good call.
Resume share.
Yeah.
No, it will not. Okay. Let me try sharing me.
Can you just share your
Yeah. Zoom. Share screen. Desktop. All right, and let me pull up the correct. Awesome. Current slide. Sorry about that.
No worries. We also only have a couple more minutes.
Yeah, well, that's okay, because I'm about to finish. Yeah. So we create a telluric template, create a stellar template. These are used as initial guesses, and we can use Wobbly as normal. And the results are really, really promising. This is an example of CI tau. I use this because, as I showed earlier, we had done the atmosphere for CI tau B. So I've done these telluric corrections painstakingly. So I know they're as good as can be done with an A0. And our correction was Wobbly, which I'm calling Wobblier because it's Wobbly in the IR. In purple, it's actually better than what we can do with an A0. With the added benefit, we don't have to take up extra telescope time. We get similar results for HD 189733 with those CO lines popping out. There's still issues to be worked on in that methane band. As I said, with the methane-water combination, it's tricky. But the CO region is looking really, really clean. And I'm very excited about this. Yeah, we're also able to do, so for HD 189733 and CI tau, we had dozens of observations. For this baby planet host, we only had 11. And we're still able to pick out the CO lines. Wobblier does a good job of picking out the stellar signal from just 11 observations. And because of that, we're able to measure the magnetic field, well, detect it, and working on measuring the magnetic field of the host star. So future work, so this was done on Igran's data. The future, we're going to try to work on more on other instruments. We're hoping to go to a more stable spectrograph. And the future is to hopefully get down to, right now it's done on RV data that requires large barycentric velocity shifts across the set. We're hoping to minimize the data requirements. All right. In summary, studying exoplanet atmospheres at high resolution is hard, but useful. We're able to find really awesome stuff like chromium hydride and WST-31b, and we're, in many cases, most cases, we can distinguish stellar activity from a planet signal, which is a huge advantage. Stellar activity complicates our analysis, but we're making a lot of progress in that area. And the future of telluric corrections in the infrared is data-driven. And with that, I'll take any questions.
Awesome, great talk, Laura. So we don't have too much time, but we could get in 1 or 2 questions. I'm going to give preference to the folks online. So if you're online and you have a question for Laura, if you can just raise your hand and come off mute. If not, we can also take a question in the room. Yes, do you mind turning on the microphone right there, just so people online can hear you? Sure. There you go.
So on the slide where you showed chromium hydride,
Yes.
Another deep molecular feature just to the left of it, which I think is
Iron hydride.
iron hydride.
Yeah,
so
they're at the same place.
is there only one temperature range where the chromium hydride works because the iron hydride contaminates it?
No, I mean, they work at comparable wavelengths. I mean, I think it's very, very similar chemistry. And they both work, they're both used for this very similar brown dwarf regime. And they're right next to each other.
I think Avi has a question online. Avi, do you want to go ahead? I think you're muted.
Great. I don't know if you can see me though. I think I am on the wrong camera.
Yeah, I can move you over.
There
We
go.
can see a little version of you. Go ahead.
Okay. Great talk, Laura. Really nice. I was particularly interested in the stellar activity analysis for TRAPPIST-1. I was interested in the sort of color or chromatic variation you see that sort of seems uncorrectable right now. Are you doing a joint fit for sort of all components here, such as, you know, the atmosphere parameters as well as the stellar variability and flare parameters, all of this, or are you sort of doing, you didn't have really time to kind of get into it too much, but how are you kind of, it's a very complicated joint fit. I wasn't sure how far you had gotten.
Yeah. Right
Oh.
now, we're doing them separately. We're doing, first we do a shorthand transit model, then we do the flare model, then we go back and do a better transit model. We're thinking about doing it simultaneously because that would obviously be ideal, but it's also computationally a nightmare because we're fitting the flare in each time bin separately, and we're fitting the transit in each wavelength bin separately. So to do both together, we'd have to fit the entire data set at once, and that's a lot of data, and we're not sure how that's going to work computationally. Obviously, that is the long-term goal, but we have we're at a computational bottleneck right now, and so it's not quite working.
Okay, yeah, that's what I was afraid what's going on, but
Yeah.
it's good to hear that. Okay, well, good luck. I would love to see how this works out. So, yeah.
Well, I think we will stop there just for the sake of time, but Laura's around this afternoon if you want to ask any other questions. But let's thank Laura again for a great talk. All right, and I'm going to end the call. Thank you folks online who came out today.